Oz is a programming language with its system, Mozart, that has flourished from the mid-90s for about 15 years. It has been developed mainly by two groups, one in Saarbrücken, led by Gert Schmolka, and the other in Stockholm, led by me, Saif Haridi. Its further development has been taken up by Peter van Rooij at Louvain-la-Neuve. Peter was a member of the German group in the early development of the Mozart and the Oz system. Peter and I will give a presentation of the origin and the history of the Oz project, the approach we took for designing the language, and what we think as its novelty, its impact, and the successes and failure of the Oz project. From the outset, I can say that Oz is a quite novel language that's very different from its contemporary languages at the time of its inception. Actually, it might have been invented in the wrong time, as it fits very well in the age of cloud and cluster computing, where concurrency and distribution is prevalent, as we will explain.
My name is Peter van Rooij, and I will start our story by going back into time. I'll start with the prehistory of Oz. It starts in 1970. Prologue, logic as a programming language. This then split into two research areas, concurrency, logic for concurrent programming, and constraints, logic for search-based constraint solving. These two areas stayed separate until 1990, when they were unified both theoretically in the concurrent constraint calculus and practically in the AKL language and system, and this was the direct ancestor of Oz and multi-paradigm programming. Let me now tell you a few stories. The first story, the French connection. The place, Marseille in France. The time, the early 1970s. An opinionated French computer scientist sitting in a bar drinking his pastis. Next to him, a dignified Englishman drinking his tea. I'm talking about Alain Kolmarauer and Bob Kowalski. Lightning strikes. They invent programming in logic, the Prolog language. An old dream finally realized. Now let's go to the east, land of the rising sun. The place, Tokyo, Japan. The time, the early 1980s. A lanky computer sensei, slowly sipping his sake. Next to him, a samurai of fast systems chugging on his acai. I'm talking about Kazunori Ueda and Takashi Chikiyama. Lightning strikes, concurrent logic programming, and they did the foundations for the theory and efficient implementation of concurrent logic programming.
We will now discuss the vision and the foundation of the Oz project. From the outset, we wanted to develop a language that supports multi-paradigm programming. The motivation was like this, that all large programs needs more than one paradigm. The program may have a database with relation structures. It may do functional transformation, and it can use object-oriented principles to structure its data and concurrency to connect its parts. So we would like to support this. How can we do it and where to start? The starting point of the Oz project is that we want to design and implement a single language, and we used concurrent constraints as its semantic foundation. So let's start and ask ourselves, what is a paradigm? And even is there such a thing that is a paradigm? Programming, as we know, is a huge bag of languages and concepts, and in practice, there are different ways of programming a computer. For the Oz design, we define a paradigm as follows. A programming paradigm is an approach to program a computer based on a coherent set of principles or a mathematical theory. We can see this in a number of languages. So functional programming is based on lambda calculus. Logic programming is based on former logic, such as Horn-Close logic. And object-oriented programming is an approach of organizing data and its operation based on abstract data types, encapsulation, mutable state, and polymorphism. So why do we need a single language? Why not just use different languages or library? By using different language or libraries, this will facilitate upward migration from existing systems. Many examples exist, and here is a contrasting example where G-code, a constraint solver written in C++, it's a library, and it is part of a programming environment for C++. It has a completely different model from C++ because C++ is a more imperative style, whereas the constraint solver is a more declarative style. This approach has disadvantages. The first important disadvantage, if we are using different libraries with different concepts or different languages, this will increase the load on the programmer. And of course, it will increase the system complexity. Another disadvantage, which is not well appreciated, is that writing in different language or systems or different libraries will make cross-paradigm optimization extremely difficult. Okay. So we thought that this is not a long-term solution, and as a researcher, we aimed for a fundamental conceptual solution. So what is the foundation of OS? How do you combine different paradigms like functional programming based on lambda calculus, logic programming, and first order logic, object-oriented on data abstraction and polymorphism, and concurrent programming in a single language? So we needed a foundation in which all these paradigms can fit naturally. And we chose concurrent constraint as our foundational model. So why concurrent constraints? All the four paradigms can be done in a straightforward way, as we will show. And it has powerful properties. Constraint domains can be defined separately, and synchronization is defined, as we will see, as logical entailment. So this will fit with the logical part of the language. So what is the concurrent constraint model? Concurrent constraint model is a calculus for general computation. The model consists of a shared constraint store observed by a number of agents. These are concurrent agents. The constraint store itself consists of a conjunction of primitive constraints, which is a solution, satisfiable conjunction of primitive constraints. And there are two basic operations that are performed by an agent. A tell C adds C to the constraint store, which become sigma in conjunction with C. And an ask operation will wait until the constraint store sigma has enough information to decide either C or not C. Technically, the ask is doing logical entailment, which checks if the constraint store sigma entails C or the constraint store sigma entails not C. So all agents are programmed in a small language. The basic operation is the ask and tell, and then we have concurrent composition, variable introductions, and procedure definitions. Just to show you a simple language for concurrent constraint, this is a simple language. And what is this language? It allows concurrent, so the language is statement-based, as you can see. It allows concurrent composition. These two statements are run concurrently. It allows introduction of variables, telling a constraint, and then a conditional that consists of a set of clauses. And if one of these clauses is satisfied, because a clause is what we call an ask clause, then it will execute. Otherwise, the S will be executed. Then we have procedure calls, which is basically starting an agent. Okay. An ask clause asks the constraint store if C is entailed, and if that is true, then it will execute S. And here is D, which is a procedure definition. The idea of concurrent constraint programming was introduced by Vijay Saraswat And this was one of his many formulations in his ACM Distinguished Dissertation Award. Here is a small program. This is defining an agent. This agent takes as input incrementally a list, so you can call it a stream, and produces another list. The elements of L2 corresponds to 2 times the corresponding elements of L1. And here is the definition of it. And here is a simple program which consists of 2 agents, the blue agent and the green agent. The idea is that the first agent initially suspends because the store does not entail L1 equal near or L1 equal the cons consisting of a head X and a tail M1, or its negation. The second agent here, the green agent, will build L1. And as L1 is being built incrementally, the first agent, which is the blue one, will also incrementally build L2. So this is, you can see here, the synchronization based on ask or constraint entailment. So the point I want to show here is that synchronization as logical entailment. So synchronization is when one concurrent computation waits for another. Logical entailment is used to define synchronization. So if we have a constraint store that consists of 2 variables that are unconstrained at this point, to do an addition y equal x plus 1, we must know x. And in fact, this implies that we are asking an operation here, asking if x is a number, then y is equal x plus 1. X is a number is a question of asking the constraint store. Does the constraint store entail that x is a number? Okay. So this is a data flow behavior. Knowledge about x drives the computation. That is a very important concept in OS. Because data flow concurrency is the core of OS, and data flow variables are the glue that ties together concepts from all paradigms. Consider this sequential OS program. This is a sequential OS program because in OS, execution is sequential unless it is created in a thread. And OS supports lightweight threads. So here's a thread. This is a sequential execution. We introduce the variable y, and y wants to do an addition on x. And this computation will suspend because x is unbound, and because of this ask operation. When x is bound by another thread, the tail operation, like x equal 5, then the computation continues.
Let me now explain the road that led from this vision to the actual system. It started when we wanted to unify the 2 areas of logic programming. So we had on the one side concurrent logic programming, on the other side constraint logic programming, and they were disjoint research areas in the 1980s. So a major problem in research was how to unify them, how to define a single model that could express both of these different approaches. This would combine reasoning systems from the constraint side with parallel computing systems from the concurrency side, leading to systems that would consist of a society of independent reasoning agents, kind of inspired by Marvin Minsky's Society of Mind. The AKL project was the first successful unification. It defined a model that composed search and concurrency arbitrarily and also built a high-quality system that successfully demonstrated this. So AKL can be seen as the Swedish ancestor to OS in 1990. So the AKL project was defined with this explicit goal, unifying concurrent logic programming and constraint logic programming. And the system that was realized was released in 1990 for both single processors and multiprocessors. The main concept in AKL that lets it solve the problem is the notion of a computation space. And each space consists of a store and its agents observing the store. And the interesting thing is that an agent can itself be a computation space, so that agents will see their enclosing stores. But agents cannot see into the minds of other agents, but they can see the environment that they're living in. This gives a full compositionality of search and concurrency. First-class search engines can be run concurrently in a concurrent setting, and on the other side, a search engine can, inside of itself, be defined using concurrent computations. Oz was the German step after AKL, so after 1990. Oz is a direct successor to AKL. But with respect to AKL, Oz has a much richer set of concepts. Also, Oz has a kernel language that's layered, letting you factor the different parts of the language, the different approaches. Compared to AKL, Oz adds the following things. So all language concepts are fully compositional. The syntax is also fully compositional. This is a break with AKL's Hornclough syntax, which still kept the tie to Prolog. So Oz broke that. Oz also provided higher order programming and ubiquitous first-class values. All the concepts in the language were available as first-class values. Oz also provided mutable versus immutable types as a first-class concept for the programmer. So the Oz language was designed in different cycles. So in 1991, the initial language developed in Germany, which didn't really have a name, which we could call Oz 0, did not yet use the concurrent constraint model. But then the first true Oz language, Oz 1 in 1993, this one was directly influenced by AKL, and this one adopted the concurrent constraint model. And at that point, the Swedish and German groups joined together to increase their critical mass, and they started working on a common system. And this led to the Oz 2 language in 1996. So this was actually the first really true Oz language that succeeded in the multi-paradigm vision. And then up to 1998, this language was extended for practical programming, adding components and support for distributed computing. I can give a more detailed timeline up to the first release of the major system called Mozart 1.0. So it started in the Hydra project in Germany, led by Gerd Smolka in the DFKI, which was a German research center for AI. And the idea was to do complex deductive problem solving. Then there was a European project called Acclaim from 1992 to 1995, which was led by Seif Haridi from the Swedish Institute of Computer Science in Sweden. And the goal was advancing concurrent constraint. So everything was built around concurrent constraint. And there were many partners, but in particular, there was the DFKI, there was SIX, and there was Digital Paris Research Lab. And there were 3 languages that were kind of living in the same space: Oz, AKL, and Life by Hassan Naid-Kaisi. And in the Acclaim project, we then made Oz 1, which was the first language where we experimented with many of the features of Oz. And there were some workshops, informal releases. So the DFKI Oz 1.0 release in January 95, the WOZ 95 workshop. And after the end of Acclaim, the German and the Swedish sides continued to work together, and they each defined a national project. They were both called PERDIO. They both got financed in Germany and in Sweden. And Peter Van Rooij, who was originally at Digital Paris Research Lab, he moved to DFKI, and then he went to UCL in Belgium to become professor there. So during this period, the first-class computation spaces and constraint programming support was added, mainly by Christian Schulte. There was also the first stable Oz language, Oz 2, in 96, and then Oz 3, the conservative extension with components and distribution for large-scale programming. And there was a release of DFKI Oz 2.0 in September 96. And then finally, the Mozart 1.0 full system, and I can remember the push for that release. This is a system with a major engineering effort behind it, 180,000 lines of C and C++, 140,000 lines of Oz, and in January 99, the Mozart 1.0 system was released. I can still remember when that happened. And here you can see some of the web documentation. There was a full set of libraries. It was released as open source with a BSD style language. And in the 2 years 1999, 2000, and 2001. Since its release, we had more than 10,000 downloads of this system, and during the decade up to 2009, it was a widely used system. And the last major release of Mozart was Mozart 1.4.0 in 2008, and this is the release that had the most functionality, constraints, distribution, and all the multi-paradigm support.
We will describe now briefly the design approach that we have taken in the OZ project. If we look to language design approaches, there are two basic approaches to design a language. One way is to start from the machine and build a language on top. This is a bottom-up approach. Examples are Fortran, C, C++, and recently Rust. This is basically a bottom-up approach which takes efficiency as a first important factor that you want to achieve, and the other is be able to control the resources of your machine. The second approach is to start from a conceptual model or a principal design and implement it. Examples are Lisp, Prolog, Smalltalk, Erlang, Haskell, Python, and Oz. And this is basically a top-down approach, which we can call the principle-first approach. Oz design approach is a form of top-down, and it is actually done in two different levels. We design a lean kernel language. A lean kernel language is based on the concepts of procedures as first-class values and the constraint store, and add few concepts at this kernel language on the top of that to be able to support what we want to achieve. So, for example, to be able to do problem solving, constraint solving, and search, we introduce first-class computation spaces, and that will be explained a little bit later. To be able to do functional data flow, we introduce thread, and we, of course, the data flow variables. These are the basis of Oz. We can have components, object system, and lazy evaluation. The object system is based on allowing mutable abstract data types and also sequential composition. On the top of that, we have a rich language. So the general language is very rich. It's rich in syntax, yet the kernel language was kept extremely small and well-defined semantics for it. The developers continuously introduce new abstractions as solutions to new problems. This is linguistic abstractions. A new abstraction is accepted if its implementation is efficient and its semantics is simple. This methodology achieves the goal of multi-paradigm programming, as we will continue to see. So let us first understand what are the basic concepts in Oz that is differentiating it from a concurrent constraint language. We have seen this slide before. So in Oz, here are the main changes, and this is done in red here. Instead of having a concurrent composition, we have actually a sequential composition. And concurrency is introduced by decorating any statement as a thread. This will introduce a thread to execute this statement. The second most important aspect is that whereas the concurrent constraint language was first order language, this is a language that allows higher order procedures. So procedures are values. That is very important concept. Procedures are values, and they are added to the constraint store. So Oz made two major changes to the concurrent constraint model. Higher order procedures, the procedures are constraints, and concurrency is explicit. And of course, all of these are coordinated together by data flow computing, okay, data flow variables. If we look to the language as a whole, it has a rich general language. So from our powerful foundations, which first-class values, we have functions, procedures, classes, object, components, module, and spaces. All these as first-class values. These are values. And then we have a compositional factor syntax, which allow you, for example, to program on the functional part and preserve the functional properties or the data flow properties of a functional program. And then we have lightweight threads and data flow variables, and we have deep embedding of distributed computing that we will discuss later. From this, we can have all these kind of paradigms. We can do functional programming, functional data flow, lazy functional data flow, actor data flow. This is very important, actor data flow, and we will explain that later. We can do all various types of data abstraction, polymorphism, and inheritance for object-oriented programming. We can have data flow concurrency, multi-agent programming, shared state concurrency, and then relational programming, constraint programming, and programmable search engine. This is a very important aspect, programmable search engine. This is a concept which Prolog did not have. We're allowed to do programmable search engine, even parallel search engine within the language itself. Here is just a quick slide of the kernel language. We can see one important aspect of this. Actually, this part of the language, the so-called functional part, this is the kernel language, not the user language, not the user language. This part defines what could be a functional program. Each program is a sequential functional program. By adding one single concept, thread end, we can support functional data flow computing. It's a parallel functional programming, basically. By adding weight needed, this is kernel concept, we can do all lazy functional data flow computation. By adding the notion of first-class spaces, we can do relational and constraint programming, and we have adding exceptions. By adding a simple concept of message passing, which is by the notion of a port or a named stream, we can implement all kind of active object and agents and actor system. And by adding containers for mutable state, we can implement all mutable abstract data types. So this is stratified, and we can say it here. We start with a simple kernel language that underlies our first design, the functional programming. Then we add concept one by one to give other paradigm. Vastly different paradigm have quite similar kernel language. The final kernel language is much simpler than the sum of all paradigms. And it is possible to program in each paradigm separately or to combine them when it's necessary.
Let me show you some of the salient features of OST. Here is a simple functional programming. You can see it's pretty standard. I have a function ints, which creates a list of integers from n to max using if statement. I have a function map that uses a case statement to map elements of a list element-wise by a function f. Delay of 1000 is just a 1000 millisecond delay, so we can see the program executing. So how does this work? Well, let's run it. L1 is ints from 1 to 10. L2 is mapping it. This will display with the browse a list 149 up to 81. Now note there is something interesting going on here. Because of data flow variables, both of these functions are tail recursive. If you look at the recursive call here, f of x, a bar, map mf, this is actually executing by first calling f, creating a pair, a const cell with a unbound variable as the tail, r1, and then doing the recursive call. So this is actually tail recursive, and it's because of data flow variables. Let's now move to concurrency, functional data flow. We do this by using streams. Well, a stream is just a list that ends in an unbound variable. So S, for example, equal A bar, B bar, C bar, D bar, S2. And you can extend it by binding S2. Now, this kind of stream can be used as a communication channel between two threads. The first thread will add elements to the stream, and the second one will read it. So here's the same program we saw before. I run now ints and map each in their own threads. So what's the difference? Well, this will turn a batch computation into an incremental streaming computation. In fact, any functional programming can be made more incremental by adding threads anywhere, and this does not change the final result. So graphically, we can have this process on the left, which is kind of an agent, creating incrementally the stream L1 and the other agent on the right doing incrementally the map. So we have two agents communicating concurrently through a stream. Let me now show a demonstration. We give a demonstration of data flow synchronization. I first create two unbound variables, x and y, and I display them in a record. Notice when I select and execute this, it will execute in its own thread. Notice that the compiler has shown that it has accepted this, and I've displayed a record with two unbound variables. I now, in another thread, do y is equal to x plus 1. This addition will not complete. It's because x is unbound, and in fact the display does not change at all. Finally, in a third thread, I will do x is equal to 5. This will cause both x and y to be bound. The addition is now able to complete. We now show a demo of functional programming leading to functional data flow. We first define two functions, ints and map. Let me compile them. Ints creates a list of integers from n to max, and map will apply f element-wise to elements of a list. Notice that both of these functions are tail recursive because of the data flow variables. We will now run these programs. This is a program, first a sequential functional programming, first creating integers from 1 to 10, and then mapping the integers. Notice that we have added a delay of 1 second so that we can actually see the program running. So let me run this. 2, 3, 4, 5, 6, 7, 8, 9, 10. So you see, notice that the result appears after 10 seconds. This is normal behavior for a sequential program. Let us now run exactly the same functions as a concurrent program, each function in its own thread. Notice that whenever int adds one element to the list, that the map will be able to continue a part of its computation. So the lists actually become streams because they're created incrementally. Let me compile this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice that each second we now get a result. So the data flow has converted a sequential batch computation into an incremental computation, giving exactly the same results. Oz has extremely lightweight threads. Here we show a Fibonacci definition with two recursive calls. The first recursive call, fib of x minus 1, is running in its own thread. Because of data flow synchronization, the results are combined correctly. So this is an extremely concurrent program. Fib of 26, you can see, generates 121,586 threads. And this includes threads that the system is using. And the total execution time is 2.8 seconds. And this was in 1996. In fact, any expression can be executed in its own thread without changing the results. Now let's see about multi-agent programming. We want to do multi-agent programming in the style of Erlang, where agents are sending messages to each other. This cannot be done in functional data flow because it's non-deterministic. For example, two clients sending messages to a server, that is non-deterministic. So we cannot do it in functional data flow, but in order to do it, we need a new concept. So we add one new concept to the paradigm we saw before, which is called a port. And it's just a named stream, as we saw before. So here on the left, in this code, a new port will connect the name P to the stream S. And here on the left, I have the thread reading the stream S with a map, just as before. But now I can have two threads, or agents, each of them sending messages to the stream. S1, send PX, and S2, send PX. So graphically, we can see that there are three processes here, and the port is receiving messages from S1 and S2, and they are being interleaved and passed on through S. In fact, multi-agent programming as a paradigm is simply functional data flow paradigm plus ports. You can see how adding one concept to a simple paradigm will give you another paradigm. Here's another example of this. The function newActive will take a class and an initialization call and create an active object that also is an object-oriented object. So the object is created using a class, and it's running inside its own thread. It has a port. So in fact, we're combining multi-agent with object-oriented programming. We're actually combining the abilities of these two paradigms. The active object has the concurrency behavior of an agent and the computation behavior of an object. Let's show something more complicated. So this is a software transaction manager using strict two-phase locking with ordered timestamps for deadlock avoidance. So the code I'm showing you here is the full implementation. Why am I showing you this? Well, I just want to show you what big, complicated Oz algorithms look like, so you can get some idea. Let me give a demonstration. This is a demo of the software transactional memory we saw in the previous slide. First, I will create a transaction manager, trans, and also a primitive for creating the new cell. Second, I will create an in-memory database with 1,000 cells. Third, I will define a transaction that scrambles the entry's values. Notice that every entry has a value which is the same as its index. 1, 2, 3 up to 1,000 has values 1, 2, 3 up to 1,000. I will now define a transaction to sum all the entries. This is using another entry that is outside of the database. And now I will first run the sum transaction before I do anything else. Notice on the left here, you see the result, which is 500,500, which is the sum of integers from 1 to 1,000. Now I will create 1,000 concurrent transactions, each in their own thread, each of them will scramble the entries' values. And finally, I will now show the result of summing all the entries after running these 1,000 transactions. Notice that the result is still the same. The transactions have kept the invariant. Let us show the first 10 entries of the scrambled database. Notice that they are fairly scrambled. Finally, here is a parser specification in Oz using the GUMP parser generator. The main specific language is defined here, creating an LL1 parser. So this is just an example of one of the tools provided in the Mozart system. Let me now talk about constraint programming. Mozart 1.0 has a substantial support for constraint programming. Constraint programming is a tool for solving complex combinatoric problems. You can see it as a kind of glue for operations research algorithms. Problems are specified as logical relations and solved with an incremental solver. And this fits naturally in the concurrent constraint model of Oz. This was mostly done by Christian Schulte with the help of other people. At its release in 1999, Mozart was the most advanced constraint programming system existing. It had first-class computation spaces to allow programming of custom solvers in Oz, and it supported nested constraint solvers, as in AKL. An example of the innovation in Mozart 1.0 is the Explorer tool for interactive exploration of a search tree. So at the release of Mozart 1.0, this was the only such tool existing.
Distributed computing in Oz. The work on distributed Oz started in 1995 and was part of the Mozart 1.0 release in 1999. It is based on a clean separation between immutable data, data flow variables, and mutable data in Oz. This separation facilitates deep embedding of distribution. What is deep embedding? Each language entity is implemented with its own distributed algorithm or protocol, which define the network behavior and failure behavior while preserving kernel language semantics. Distributed behavior of a general entity, like object or classes, follows from the distributed behavior of its kernel language parts. Application behavior is independent of the distribution structure, except for operation timing and partial failure, for which extensions were provided. So distributed behavior of a general language entity as defined in terms of its kernel language part actually became very successful. It allowed a modular design of the distributed implementation of OS. So let us look to distributed objects in OS. Here is a definition of a class. The class is account and an object A that is created by starting with a transfer of 100. The object distributed behavior is defined by the distributed behavior of its parts. An object consists of an object record, which contains a class and the object's mutable state. Each object record and its class are immutable, which means they can be copied across the network. Mutable state obeys a consistency protocol. Methods are procedures, hence values, inside the class record, because procedures are values, that's fine. Uniqueness across the network is handled by the unforgeable name of the class. And a name is immutable and globally unique. What is the composed distributed behavior of the object A? Once an A is remotely referenced, the object record is copied to the remote site. Since the class is uniquely globally named, the class and its records of methods, which are procedure values, are only copied if they do not exist on the receiving node. The object state follows the protocol of mutable values, which guarantees the consistency of the object state in case multiple threads are accessing the object. The overall behavior here is that objects migrates to the node where its state is modified. Stationary objects behavior can be implemented by hiding the object behind a port and behaving like an active remote object. Another interesting protocol is that of data flow variables. This figure shows how a data flow variable is distributed over 3 compute nodes. This behavior generalizes remote futures that allows broadcast and maintains consistency of the distributed constraint store. Binding a data flow variable to different consistent values will always lead to the same result, no matter in which order the data flow variables are bound. This is a consequence of the semantics, which is distributed unification. Once a data flow variable is remotely accessed, a manager M and a set of proxy structures, Ps, are created. When a variable is bound, the manager broadcasts the value to all the proxies and the master proxy structure disappears. This is the generalization of future, which allows one-to-many broadcast of the binding of the data flow variable.
It's interesting to see some of the important OS applications that were written. So here's a table showing the largest applications that we know of and in terms of how they use the strengths of OS and the Mozart system. So Strashila is a tool for computer-aided music composition based on constraints. BeerNet is a structured overlay network based on a relaxed string. Dive is a distributed virtual environment. TransDraw is a distributed graphic editor based on transactions. Omega is a distributed proof assistant for mathematicians. Logos is an environment for teaching programming based on progressive enrichment of multi-agent microworlds. There was a programming textbook, Concepts, Techniques, and Models of Computer Programming, published by MIT Press in 2004. Fairly big thing, 929 pages. The chapters are organized according to the paradigm, so the approach that we used in designing OS was made very clear in this book. The main theme of the book is concurrency, which covers about 1/3 of the book. This book has got good reviews. So, for example, Peter Norvig has a very nice quote on the book showing how it basically is a successor to the well-known book by Abelson and Sussman. So, we used Oz in programming education. Here are, in the left, 5 paradigms that we teach in our course. We were teaching this in university-level programming courses at KTH in Stockholm, NUS in Singapore, and UCL in Belgium. Also at UCL up to the present day have been using it, and we know of at least 16 universities that are using it worldwide or used it. It uses a concepts-based approach for teaching programming, where concepts are introduced progressively in paradigms, and we give formal semantics for all of these paradigms. There were also MOOCs on the EDX platform, Louvain 1.1x and 1.2x, over 5 years. SimX is an architecture simulator. It was the first system-level simulator that could boot a non-modified commercial operating system at the instruction level. And at that, it was very interesting for people designing workstations and computers. The core of SimX is a tool called SimGen, which was written in Oz on Mozart since 1997, compiles an architecture specification into the components necessary for its operation. So in the diagram you can see that there's articles on it. SimGen is still being used today. So now today, as I'm speaking, by Intel. And it's running in Mozart 2. It's probably one of the longest lasting projects that use Mozart. iCities was a European project from 2001 to 2003 to study emergence in online communities. So it did very large, extremely concurrent simulations. It used Oz and Mozart to do these parallel agent simulation for clusters. In 2002, we were running it on 16 AMD Athlon computers with 100 megabit Ethernet, achieving a fairly good speed up. So this was state of the art at the time it was running. The Friar Tuck is a round-robin sports tournament scheduling application. So it shows you a part of its interface. Initially implemented in Oz on Mozart in 1999. It won a prize, actually. This software has actually scheduled several real-world sports tournaments in England and the United States. The company that was formed for this still exists today, and it's called Workforce Optimizer. Oz was used in natural language processing, and there was a 323-page book for computational linguistics in Oz, published in 1999, and the main author of that was Denis Duchier. So here's some chapters: chart parsing, context-free grammars, unification grammars, semantic underspecification, dependency structures, dependency parsing, concurrent chart parsing, so symbolic manipulation of natural language. It's been 30 years since the beginning of the Oz project. What can we conclude from this? Well, in terms of successes, the initial goal of multi-paradigm programming was largely achieved. The Oz language successfully integrates many paradigms, and the Mozart system is a high-quality, efficient implementation. The Oz approach to concurrency successfully simplifies writing concurrent applications. The programming textbook successfully presents programming as a unified discipline integrating many paradigms. The book and Mozart system were successfully used in education. The Mozart system was successfully used to build large applications. The deep embedding approach of Oz for distribution is practical for cluster computing, and Mozart 140 is a high-quality system that successfully combines multi-paradigm programming with constraints and deep embedding of distribution. So that is a number of successes. Unfortunately, there were also some failures. So now, with the looking back, we noticed that we failed in creating a self-sustaining community. After 2009, the community dropped. And the reason is that we failed to navigate the transition between funded research and open source development. Most of the key developers left the project and were not replaced. Open source culture was in its infancy when Mozart was first released, and we did not realize how to manage that. We also failed to navigate timely the transition to 64-bit architectures due to lack of resources. and funding support for programming research in Europe diminished, which did not help us. Also, the Oz syntax was an unusual one, and the object syntax in particular was not polished. So this created a threshold for new users to join the Mozart community, and we failed to recognize this and modernize the syntax. What is the legacy now of this whole project? Well, Oz was a pioneer in many ways. In programming education, Oz was and is a successful foundation for a concept-based approach. Oz also pioneered several important programming concepts: lightweight threads with shared data, data flow variables as a tool for fine-grained asynchronous programming, the distinction between mutable and immutable data types, functional data flow, which is now a standard paradigm for streaming analytics, programming with actors and futures together, which is now quite widely used, techniques for efficient constraint solving, including computation spaces, were pioneered in Oz. And also the deep embedding of distributed computing was successfully pioneered in Oz. And I would like to end by giving a tribute to all the people over the years who contributed to building the Oz language and the Mozart system.